Okay, good evening, everyone. So I just want to quickly check if you can hear me on Zoom. Okay. Can you see me also on YouTube? If someone is currently on YouTube. Okay, perfect. Okay, then let's start soon. And can you hear me well in the back? Good. Okay, perfect. Okay, so sorry for the delay. So welcome everyone for lecture 5 of EML. So last week we basically introduced classification problem, right? And we sort of discussed the few distinction between regression problem and classification problem. So the key distinction between regression and classification is that your response, the output Y in regression is usually quantitative. Whereas in classification, the response is what we call qualitative, right? So it can take on a discrete number of value or finite number of values. And now the question is, can we use regression for classification tasks, right? The answer is depends, right? For most of the binary classification, where you have just two classes, you can use regression to solve this, but it's not going to be the best model you get. Why? Because why can't we use regression to solve classification? Right? So the main distinction, I think, if you remember from last lecture, is that in regression, we want to also take into account the ordering of the output, right? Whereas in classification, the ordering of the output doesn't really matter, right? If you have two classes, let's say cat and dog, right? We don't have the ordering of these two classes, right? Whereas if you have, let's say, the output that represent sales, then basically we should respect the ordering, right? The higher the sales, the better in this sense, right? So that's the key distinction. And we look at how to fit logistic regression, right? So logistic regression is sort of also similar to linear regression. The only difference is that you're now applying the logistic function on the output. And basically, what you're doing is essentially you're regressing from the predictor to the outcome, where the outcome now is the probability of the predictor with that particular value belonging to specific class. Right? And at the end of the last lecture, we look at the different way of doing classification. So in general, in machine learning, we have categorized classification into two categories. First is called discriminative. The second is called generative. Right? What it means to be discriminative? Discriminative approach means that you're giving a class of data, right? Training data that have, let's say, two classes. And discriminative approach basically just try to find a discriminator, right? Discriminator in this case could be just a line, right? That separate these two classes. Right? But the idea of the generative approach is that given two classes of data, let's say cat and dog, right? Instead of trying to find the separator, right, in the space that the data live in, you first try to model how the cat look like, and then also model how the dog look like. Right? It's generative in the sense that you're trying to model how the data look like in different classes, right? And then when you want to do classification, let's say you're given a new image, right, of something, then you try to compute what is the probability that that image belong to the cat, and then also compare that with probability that it belong to the dog class, right? And then based on that probability, you try to make decision, right? Whether we should classify this image as a cat or a dog, right? And that's the essence of generative approach. And that's something we are going to look at today, okay? So, I mean, just to give you an intuition, let's say, I mean, just to compare to how human learn, for example, like when you encounter different kind of animal, right? The way that you would recognize the animal is basically by observing the animal a number of times, right? I think in our life, we see a number of cats. We understand how cat look like, right? Then we have a sort of a good model in our brain how cat look like. We also have a good model of how dog look like, right? But then when we encounter, let's say, a different animal, right? We use the knowledge that we have learned in the past to somehow compute, right? To see, oh, how should this data fit, or the new animal, should this animal fit into the category of cat or dog by using the model that we have stored in the brain, right? So in a sense, we are doing kind of learning throughout our life by observing object in the real world, right? And now the question is, how can we teach machine to do that, right? And the tool that we are going to use is very popular in Bayesian classification. It's called Bayes formula or Bayes rule, right? And we call that, what we are trying to estimate in logistic regression is this quantity, right? This quantity, which can be interpreted as the probability of the outcome y given the input x or the predicted x. And in logistic regression, we estimate this quantity directly. But in Bayesian classification, what we are going to do is that we're going to use Bayes formula. So this quantity, the conditional probability of y given x, can be expressed, right, as a product of probability of x given y and p of y divided by p of x. This is basically the left-hand side represents the posterior probabilities, right? It's the probability of the output given the input. This is the probability of p of x given y is the probability of the input given the output. And this is, we call class density, right? So what is the probability of x given that we know the class of that data point? Okay. And this represents prior probability of the output. Let's say we focus on binary classification problem. Let's consider cat and dog. Okay. This probability represents our prior probability of these two classes. Right. If in our lifetime we observe the equal amount of cat and dog in the real world, then our probability would be 0.5. But let's say in the real world there exists more cat than dog, then our probability would be biased toward cat or the dog, right? And this is just represent the prior probability of the input. And this normally is just a constant. It's just a normalized constant. So in the end, we end up not modeling this, right? Because in the end, it's just a constant. And then we can just remove this part, this term in the end. Right. So in Bayesian classification, let's say we have k classes, but let's focus on two classes just for simplicity. I think that's easier to understand. So we can use Bayes formula, right, to calculate this quantity, right? And this is how we represent this conditional probability. So this is the probability that the data point whose predictor values is x belong to class k. And this can be computed based on the formula using this. And here, so this pi k, pi sub k is a prior probability of class K. And f sub k of x is representing the class density. And the normalizing term, we can just sum over this quantity over all possible classes. Right? So it's the end, in the end, it's just a constant term, normalization. Okay, how would you interpret this? So this is the probability that x belongs to class K, right? So the probability that x belongs to class K depends on our prior belief, right, about that class, right? The density. What is the interpretation of this? If we know that what is the probability of x given that we look at class K, and then basically based on this quantity, we can compute this p sub k for all possible classes. And then what do? We pick the one that is the highest, right? Has the highest probability. That's one possibility. Right? Let's say you have two classes, then you just compare the probability that you get. Okay? And we typically we estimate the prior probability from data. How would you estimate this? Well, if you have data of cat and dog, you just count the number of cat, and then count the number of dog, and see. And then you compute the proportion of this data, then you get this prior. And this basically the rest is just something that I just said earlier. Okay. And yeah, so as simple as that, what we want is this posterior probabilities, right? We want to get the probability that the data X belongs to class K. And this can be obtained by this formula. Any question at this point?
What is the relationship between
sometimes they call like this. Yes. It's the same. Yes. Any other question? Okay. No question. Yes. Yeah. So as simple as that, but I mean, it's not as simple as that, because in the end, we need to be able, this formulation, assume that we know how to estimate Fk, right, which is class density. Right? And in general, we don't really know what is class density. So we have to make assumptions about these quantities. Right? And the first algorithm, or well, the second algorithm we are going to look at is called linear discriminant analysis. And the idea of linear discriminant analysis is to make use of this Bayes formula, but then further make an assumption that Fk is a normal distribution, of Gaussian distribution. Right? What does it mean? It means that Fk of x take this form. So this is just a normal distribution with mean mu k. So it's mu k because it's class density. Right? And sigma k also is class density. Right? So the Gaussian distribution is parameterized by these two parameters. Okay. And further assumption is that we assume that all classes have the same value. So it means that sigma 1, sigma 2, and then sigma k squared are all the same. And we're gonna represent it by sigma squared. Okay, so the variance, so the assumption of LEA is that the density is Gaussian, right? And they have the same variance across different classes. Okay, but the mean are different. So now we just basically replace Fk, right, by this quantity in the Bayes formula, right? This is what we get, and then we can take the logarithm of the numerator, and this is exactly what we get, right? So this will be the logarithm of this term. Right.
Do we do in a multivariate setting?
What do we do in the multivariate setting? Very good question.
Does mean that this vector of the quantifiers mean? Or
We will go to that. I mean, that's the next step that we will look at. But that's a good question. Yeah. So in this case, we assume that we have just one predictor. Okay. We have one predictor. Okay. So let's say if you have this, right? So you have these quantities, and you know how to compute this. Right? So this term doesn't matter. Why? Because it's going to be the same across two classes. Right? The only thing that is going to be different is this. Right? So if we want to make a classification, right, then we only need to compare these quantities across two classes. Right? And to simplify this form, we take the logarithm. So this is the quantity that we get. Right? So we actually learned that the Bayes optimal choice is basically to classify X, right, to the class with the largest discriminant. So what I mean by discriminant is basically is quantities here. It's just the log probability. Let's say you have two classes, this just becomes P1 divided by P2. Right? And if you take log of this, you get these quantities. Where delta K is defined like this. So this delta K is nothing but the quantity that we have seen before. And this term is gone. Why? Because here it doesn't really depend on anything. It's just a constant. Right? It's the same across two classes, so it's cancelled out. Right? So the only thing that we have left is this, and this term. Right? Right? So basically, because I mean, I think it's easy to think in binary classification. Right? So in binary classification, you just want to check, right, whether one probability is above 0.5. Right? If one probability is above 0.5, the other would be smaller than 0.5 because they have to sum to 1. Right? So it means that if you look at this ratio here, right? So if let's say the PK here is just P1, and then PL is just P2, then what happens if P1 is larger than P2? Sorry? Yes. So when does this term become zero? Right. So if both of them are 0.5, then what you get is log of 1, which is 0. Right. So it means that actually if one of them is larger, let's say P1 is larger, then the value of this function should be larger than 0, and then smaller than 0 in the other direction. Right? This means that actually you can identify the discriminant by setting this quantity to just 0. That would be your discriminant, the discriminant. Right? Okay, so if phi1 equal to phi2, let's say if we have equal prior over two classes, like cat and dog. So we classify observation X to class 1 if this quantity is larger than this. Where do we get this? Right. So if you go back, right? We want to basically, let's say this is 1, this is 0, this is 2, cat and dog. Right? So we know that we will assign X to class 1, right? If the probability of class 1 is larger than the probability of class 2, which means that this quantity should be larger than 0. Right? Which means if you take this and then calculate, right, the difference between two delta, then you will get exactly this condition. I mean, that's something you should try at home, right? So you take this, right, and then substitute this formulation into this, and also this, right? And then you solve for the condition when this difference is larger than 0, and then exactly that what you will get in the end, right? So the basic decision boundary is the set basically a point for which both discriminant are equal. Right? So this is exactly this point. And so this is exactly the illustration of LEA. Right? So in this case, we have two Gaussian distribution. Right? We have one predictor. We have two Gaussian distribution. Mu1 is minus 1.25. Mu2 is 1.25, right? So the mean is around here and here. Right? And we assume that the variance are the same. Right? So this means that the two Gaussian look the same, right? They just basically shift of one another. Okay? And here the dashed line represent the Bayesian decision boundary, right? At which an observation is equally likely to belong to either class. So it means that if your observation line is 0, it means that it has 0.5 probability to belong to class 1, and also 0.5 probability to belong to class 2. Right? So if you make prediction based on the highest probability, then you would classify any point that lie above this to class red, right? And any point that lie below this to class green. How would you interpret this overlap between these two distribution? I mean that I think basically the observation that lie close to the boundary has really equal chance of belonging to either one of them. You may have a cat that look like a dog, or vice versa. Okay, so in practice, we don't actually know the true probability distribution. We assume that it's the Gaussian distribution, but we don't really know what is the value of the mean, right, and the variance of the Gaussian distribution. But we can estimate that quantity from the data. So in practice, you would replace these two Gaussian by a Gaussian distribution that you would estimate from the data. Right? How would you estimate the mean? Right? Well, you would estimate the mean by just average, right? So this is class-specific average. How do you compute this? You just take, let's say for cat, right? You just take all the cat images and then compute the average of the images. Right? So you would get the average of the cat and then the average of the dog. Right? Sigma, we assume that they are the same. So you just take all the data, combine, and then compute the variance. Okay? And then what is phi? This is basically prior of k. So I think I missed the subscript here. Pi k, you just look at how many cat you have in your data set divided by n, which is the total number of data. And then basically you replace all these estimates that you get into the formulation that we have, right? And then you get this discriminant. And one observation that we can make from here is that this is linear in X. You can see this term depends on X and it is a linear function in X. So that's why we call it linear discriminant analysis. And now, before we move to the next topic, the one that will address your question, is there any other question about linear discriminant analysis? Anything that is not clear at the moment? Oh, everything is clear? Good. Yeah, just a second. Yes.
I mean, I didn't quite see how how we got from the base formula to the one applied to the classes space.
So it's not clear how to get from the formula to
the application. There was a few slides back. So
to this or to this or to this
actually one before.
one before. Okay.
Yes, this one. How we got from base methods to base classification, is that like the correct color or?
So which step is not clear? Like how do we get from the formula to the classification, right? So okay. So if I give you these probabilities, can you do classification? Why? But you can compute, let's say you have okay, let's look at this quantity. Sorry. This is the same, right? So if I give you this probability, conditional probability, then you can compute for each image what is the probability that that image belongs to class cat, and also what is the probability that that image belongs to class dog. Then you look at which probability is higher. Then you classify based on that. Is that clear or not yet? Right. So if you know how to calculate this probability, right? You just take your data, right? And then this probability will give you the number that represents the probability that that data point belongs to specific class. Let's say you have two classes. So you compute, let's say, X and then Y equal cat. That would give, for example, 0.7. And then the next step you do Y equal, I don't know, dog, right? And then you look at which one is higher. And then you classify this. It's okay. You can ask a follow-up question. It's okay.
So in the formula specifically, which of the pi k, fk, the sum to which of the different probabilities to these corresponds to pi k, fk is that the probability of the input given the output, and if so, where that the probability of the output.
So the prior probability of the output. This one, you mean?
In general, which ones from the bottom correspond to the
Oh, okay. So which one corresponds to that? Okay, this quantity here corresponds to this.
Yes, in the fraction.
In fraction, pi k represents this. Here y.
Okay.
Right. But because we have a finite number of class, two classes, then we have probability of class 1 and then probability of class 2. Right? Probability that y equal 1 and then probability that y equal 2.
because we have y can take two values, right? Either one or two, either cat or dog. Right? So we have pi one, pi cat, and then pi dog. Two numbers, and this quantities, right, represent this, right? And okay, I can give maybe we don't have explicit, but this basically just say what is the probability of x given that y equal k, right? And you will have two probability p of x given y equal cat, and then p of x given y equal dog. And in the LEA, we assume that this p of x given y equal cat is the Gaussian distribution, the same with the class dog. Okay. I hope that answers your question.
So if they are the same, the y have to be no different. dy and dry and cut.
Well, okay. So this is a special case because in general Bayes rule for any random variables, it doesn't have to be discrete or finite, or take any finite number. But y could be a real value. X could be maybe high-dimensional vector, for example. But in our case, the problem will become very simple because y basically take on discrete value, just cat or dog. So this is just a simplification of this formula. Yes.
Can we expect the whole term for L equals 1 to k to be 1?
Can we, sorry?
Can we expect the whole term to be 1 over all classes?
Can we expect the whole term to be
Yeah.
1 over all classes? Which term?
Okay, and so the pi k times fk of x divided by the sum of L to k pi L fl x.
Yes. Yes. Something. Okay, that's why we normalize. Any other question? Yes.
So from training, we always want to collect balanced data set. Does that mean always have equal number of cats and dogs so that I can give these things?
Yes. Yes. Right. So I think the prior basically represent our prior belief before seeing any data. Right? So usually people estimate this by just looking at the fraction of your data, like the fraction of cat, the dog, right? But it doesn't have to be 0.5. Like for example, in the default data set that we looked at in the previous lecture, the proportion of people who default is much smaller than the proportion of people who pay back the loan, right? So in practice, when you use the predictor that we learn from the data, you want to also take this into account that in the real world, you tend to observe less number of people who default compared to people who pay back the loan, right? And if you set this higher probability to be 0.5, this will bias your prediction, right? Because the belief that you have about the class doesn't match with the real world. Right? Okay. Okay, so that's the simplest version of LEA, but we assume that we have one predictor. So what do we do if we have more than one predictor? Right? What if we have a vector? Right, so the idea is that, well, we are not doing anything complicated, right? We just say, okay, instead of have a univariate Gaussian distribution, now we're just going to assume that the density function is the multivariate Gaussian distribution. Right? And that exactly is formulation. So here you have UK, which again represent a mean vector of class 3. So now it's become a vector, not just a scalar. And sigma represent the covariant matrix. And following the same calculation, we get that the discriminant can be expressed in this form. And in this case, we're gonna again assume that the covariant matrix are the same across all classes. So what is the difference, right, between this model and the one that we looked at before? Before we have one predictor, how many parameters we need to estimate that case? Let's say we have two classes. Two parameter? Why? You have, what is PK? The parameter is mu. So you have to estimate the mean of the Gaussian and also the variance. So there are two mean, so two parameters plus the variance is one. So three, at least three, right? If we don't talk about the prior as well, then in this case you have three parameters. But what happens if now we have P predictor? How many parameters?
The mean should then be a vector of length P. So
The mean, yes. The mean will be a vector of length P. Yes.
and the component will be probably the exponent one P of the feature.
Yes. So you have P dimensional vector and then number of class.
Then you also have the covariance.
Covariance is P by P, right? But what is the actual number of parameters that we need to
Actually, like the symmetric,
Yeah.
X and Y have a certain covariance,
Right.
and Y and X.
Right. So it's so you don't need to estimate all the element of the covariant matrix, right? So it's P times P plus 1 divided by 2. And then you have this quantity with the number of classes here. Right. So you can see that the number of parameters of the model, right, grow, right, proportionally to the number of not only the number of class, but also the number of predictors that you have in the models, right? And I mean, it can even be larger than this because here we assume that the covariants are the same across all classes, right? And the reason we use this, right, is because the Gaussian distribution, right here, the covariant metric basically models the correlation between different predictors. Let's say you have two predictors, x1 and x2. Right? So this multivariate Gaussian represents the situation when you have two uncorrelated predictors. So if you have predictors that are correlated, then your Gaussian distribution will look like this. It will no longer be symmetric. It will look like elliptical, right? Here the correlation is 0.7. Okay. So this basically allows you to actually model the correlation between different predictors as well. So this figure represents 2D synthetic data with three classes. In this case, we have three classes, and the ellipses that you see basically contain 95% of the class probability mass. Like we have three classes. And the dotted line here represents the base decision boundaries. So here we have the boundary between this class, green class and blue class, and also the boundary between blue class and orange class, and also the boundary between green class and orange class. And how do we estimate the parameter? The idea is still the same with the LDA, right? But how do we estimate multivariate LDA? We follow the same step. We follow the same procedure. Basically, we can just, I think it's not okay. We can just estimate the mean, right? And also the covariance. The mean is easy to estimate, but the covariance is much more difficult to estimate because we have P by P parameter. Any question at this point? Okay, so let's look at an example. So we looked last week at the default data set. Right? So in the default data set, we looked at a data set of people who defaulted and who pay back the loan. Right? And then we want to build a classifier that, given a balance as a predictor and also a student data, predict what is the probability of that person paying back the loan or defaulted. Okay. And if we apply multivariate LDA to this data set, the training error for LDA is still 2.75%. Would you say this is a small training error? So out of 100 maybe people, maybe you make a mistake on around 3 people, right? So it's relatively good. You know, you can use this in the real world and make prediction. Then you get rid. Yeah, but the problem here is that if you look at the data, it's highly unbalanced. As I said before, the number of people who defaulted is much smaller than the number of people who pay back the loan, right, in the data set that we have. So if we just, you know, look at the number of positive example, it's just 3.33%. What does it mean? I mean, the error that we make is slightly below this things, right? And if we actually look at, so what does it mean? Okay, so it means that actually if you build a very stupid classifier, what does it mean, a stupid classifier? It means that for every observation that you see, you're just gonna say no. And this classifier already achieved 3.3% training error, but the classifier is very stupid, right? Just say no, so it's useless. So this is something that you also have to be careful, because this is exactly the problem you have when you have unbalanced data set. Right? If you have a balanced data set, then it's fine, but in most of the real world application, you're gonna observe this kind of imbalance in your data set. You can even look at like the number of prediction or the error that you make, right, in 2 different classes. In this table, I forgot the name, but confusion matrix. Okay, yes. This is the confusion matrix, right? Basically, what you look at is that you look at the true status, the true default status in your data set, right? So in your data set, there are 333 people who defaulted and about 9,600 people who pay back the loan. So in total, you get 10,000, right? And among those who pay back the loan, right, you make prediction that 23 of them will default. So this is the error. Right? So in this class, right, you make 23 mistakes. The model makes 23 mistakes. But in this class, right, you can see that there's only 333, right? But out of these 333, you make a lot of mistakes, 253. Right? But overall, you make small mistakes. Overall, you only make 104 out of, I don't know, 10,000. Right? So that's why you observe very small training error. Right? But if you look at specific class, then you can actually, the model actually doesn't really perform. Right? So this is something that you also need to take care of. And what we are looking at, basically, they have the name, right? So this element here, we call it true negative. True negative means the true class is negative. And then the model also predict that it's negative. So it's true negative. This is false positive. False positive means the true class is negative. but the model predict that is positive. Okay? This represents false negative. So the two class is positive, but the model predict that is negative. And this is true positive. So the true class is positive, but then model also predict that it's true. It's positive. So this represents the correct prediction of the models. The diagonal term represents the correct prediction, but you can also categorize the mistake that the model made into two categories: false negative and false positive. Okay. And this is something that we can use to evaluate the model, how model perform, by looking at the two false positive and false negative. Okay. We can also compute sensitivity. Sensitivity is just the proportion of true positive out of the total number of positive. Right? This P star is the total number of positive classes. Right? So this is basically the fraction of correctly predicted positive. You only focus on the positive class and look at how well the model can perform in that class. And specificity is the fraction of true negative among all the negative examples. Right? So basically, it's a fraction of correctly predicted negative. You look at the negative class and then look at what is the accuracy in that class. And if you look at okay, what is this? This is just a stupid classifier. Let's say I'm always going to predict no. What is the sensitivities for the predictor? Sensitivity is just 0. Why? Because I'm not going to predict any positive class, right? So the true positive will be 0. Right? But what is the specificity? Well, it's just 100% because I always predict negative class, so I'm going to get all the negative class correct. Right? So in practice, you would want both of them to be high, right? You want the predictor or the classifier to make correct prediction on both classes. Okay? And what is the sensitivity and specificity of LVA? 81 divided by 333 is 24%, and then this is 99%. What can you tell from this number? What can you tell? What kind of interpretation you can make out of this number?
It's basically more fair than the multi part because it also considers the positive, the real positive. It's not only able to detect no's good, but it's also able to detect some of the positives.
Right. Exactly. So the problem is that if we can compare two models, right? The stupid model. If you compare the LVA to stupid models, it's performed better than stupid model in terms of sensitivities by giving up some of specificity, right? But still, you can still see this frequency, right, between sensitivity and specificity of the LVA. It's performed much worse in the positive class. Right? And why? Because we only have a small number of positive examples. Right? Right. So we set prior to be 0.5. I think no, not 0.5. Prior is prior respect this proportion. But the threshold that we set is 0.5. Right? The threshold that we set when we make prediction is 0.5. And that is also related to this behavior that is here. Right? So the LEA, basically the conclusion is that LEA approximately Bayes classifier, so it's minimized error on all observation. It doesn't care, right, about specific class, right? So you can have a good overall accuracy, but still you have worse accuracy if you look at specific class. And this is false positive is also called type 1 error. So if you have learned this already, this is type 2 error for positive. And sometimes it's not easy to remember which one represents type 1 error, which one represents type 2 error. So I think one way to remember this is through this figure, right? So this is type 1 error, false positive. Why is it false positive? So the doctor said, "Oh, you are pregnant," but actually this is wrong, right? And you can tell by the face of this guy that he's really shocked that he's pregnant. Okay. This is type 2 error, false negative. Okay. You're actually pregnant, but the doctor said, "Oh, you're not pregnant." Okay. And these essentially are two types of error that the classifier will make, right, when you do binary classification. Okay. Any other question? This one? Yes.
And we still compute confusion matrices and sensitivity and sensitivity when we have multiple classes, we have more than 2 classes. Because at the moment we have a true and false setting. What if there are like 5 or 10 classes?
If you have 5 or 10 classes, the question is how can we still compute the confusion?
Yeah, the confusion matrix.
Sensitivity is the specificity and sensitivity is defined with respect to just 2 classes. For multiple classes, I think we will look at a different way of computing this number. But there's a way to extend this to multiple classes. Okay. And well, as I mentioned before, the problem also comes from the fact that we set the threshold, right, when we make prediction to just 0.5, right? So for the default data set, right, we are interested in the probability that the person will default given that that person have this value of predictor. And we want the threshold to be 0.5. But we can actually, because we know now that the number of people who gonna default is much less than the number of people who pay back the loan. So we can play around with the threshold, right? So we can actually try to increase the sensitivity by choosing different thresholds, right? And this can be done by basically saying that the threshold could be smaller than 0.5, and this is gonna assign more points to class. Yes. For example, you're gonna classify that the person will default if the probability is smaller than 0.2, for example, right? And this result in this sensitivity, you can see that sensitivity increased to almost 60% compared to 24%. Okay. But what happened with specificity? You're doing worse, right? Before it was 90, 98 or 99, right? But then now, because you set the threshold to be smaller, you have to give up some specificity, right? To improve sensitivities, right? And this is something that represents also the trade-off, because if you look at sensitivity, it's improved from 24% to almost 60%, but you only give up a little bit of specificity, right? So this maybe is the trade-off that you're willing to make. Okay, and the error is now become a little bit larger, right? But that's also a trade-off, right? Okay, so this is the number with this threshold, right? And so I think the takeaway here is that let's look at so the question that I want to raise is, should we care about type 1 or type 2 error? Right? Depends on the context. Why? So let's say we have this example of a bank, right? Bank want to predict whether this person is going to default or not, right? And then use that prediction to make decision whether to give that person a loan. What is type 1 error in this case?
The default if I give the loan to the profit, then if I go with the loan,
Yes. So there are two types of error, right, that the bank can make. The first is that that person will pay back the loan in the future, right? But the bank decided not to give the loan. Right? And the second type of error is that person is going to default in the future, but then the bank decided we'll give that person a loan. Right? So which situation is more? Yes.
Depends on the index.
Depends on the index.
Charges a lot for every loan. It would be worth it to have a small type 1 error. If you have then to take into account having a large type 2.
Right. So it depends, right? Whether the bank wants to take risks or not. Usually, if the bank wants to take risks, they will try to give out as many loans as possible, even when some people is gonna default because the return is high. But if the bank is, that's why that's the reason why we have financial crisis, because banks tend to be risk seeking. But if the bank is more risk aware, they will try to limit the number of loans that they give out, right? Then they will be more careful. Right. How about the example of the medical domain? Let's say you want to build a classifier that predict whether the patient has certain cancer or not, right, from, let's say, X-ray images. Should we care more about type 1 error or type 2 error? What is type 1 error in this case? The patient has no cancer, but then we predict that the model predict that the patient has cancer. And type 2 is that the patient has cancer, but then the model predict that the patient doesn't have cancer. We want to minimize type 2 error because
if the diagnosis of not having cancer,
right. Yeah. So if we predict that someone who doesn't really have cancer has cancer, then maybe the impact of that is much smaller than like making false prediction about someone who has cancer, right? Because if we know that that person has cancer, then we can prevent him from dying. Whereas if that person doesn't have cancer, maybe it doesn't matter what we do to that person, he's gonna live anyway, right? Yeah. So this is something that it depends a lot on the context and application. How about I think this is my favorite example: criminal justice. Let's say the judge wants to use model to help make prediction about whether a person will commit a crime in the future or not. And then based on that prediction, decide whether that person should be put in jail or not. In this case, what would be type 1 error? The person will not commit a crime, but then the model predict that there's high probability that that person will commit a crime. But then type 2 will be that person will commit a crime in the future, but then the model predict that, well, it's less likely that this person will commit a crime. In this case, which type of error should we have? Type 2, which is why? So type 2 means that person will commit a crime, but the model said it's less likely that this person will commit a crime. Right? Shouldn't we care more about the first? Because if we make the first mistake has been that we put innocent people in jails. But if we make a second mistake, it's been that we let the criminal go, which is maybe fine, right? But it's not fine, but I think you have to. So in law, they believe that it's better to let a criminal go than put one person in jail, innocent people in jail. Right? So that's definitely right. And also, this is something that I think you should also take into account when you apply any kind of automatic decision making, right? Because now these days, this kind of machine learning model have made their way to all these applications. Right? It has been used in medical domain, it has been used in criminal justice, helping judges making decisions, right? So it has an impact, and I think this distinction between type 1 and type 2 error will help actually you make better judgment about whether you should put that model in the real world or not. Okay, and this plot basically just show any questions so far, by the way? No? Okay. Okay, so this plot just basically show the error rate and false negative and also false positive rate as a function of threshold that we set. Right? As you can see, if you increase the threshold to 0.5, false negative rate increases. So false negative rate just represent 1 minus sensitivities, whereas the false positive rate decreases. Right? So you have to sort of, when you keep the threshold, you have to make the trade-off between these two. Let's say if you compare here, if you decide between 0.3 and 0.4, right? Should I use 0.3 as a threshold or 0.4? Depends, right? Depends on whether this level of false positive and this level of false negative are acceptable for your application. And then you have to sort of make an adjustment here. Okay? Another way that you can use to evaluate your model is to look at what we call receiver operating characteristic curve or ROC curve. Right? And this ROC curve basically plot the sensitivities, right, which is true positive rate, against 1 minus specificity, which is false positive rate. Okay? So for different value of threshold, right? So every point on this curve represent the value of true positive rate and false positive rate for different value of threshold. So here we have very high threshold, here we have very low threshold, so here the threshold is 0.5. Okay. Usually we look at the area under this curve, right? So the area under this curve is basically this area, basically. The larger the better. Right. And if you just basically make random prediction, right? Usually what you get is that the curve should look like a diagonal line, and the area under the curve would be 0.5. So in the end, you want the model to have this ROC curve as close as possible to this point. Right? The closer it is to this point, the better. Okay. Well, the question is, what if the curve go below this diagonal line? Yes? You have some question or answer? Answer, okay. Yes. But we can correct for that, right? We just flip the prediction, and then the curve would be above this line here. Okay. Okay. So the last classifier. So far we talked about LEA. So what is the main assumption of LEA? So the key assumption is that the variance are the same across all classes, right? So the idea of quadratic discriminant analysis is to relax this assumption and to say that the variance or the covariant matrix, right, of the density function can be different as well. Okay. And this is LEA, right? So LEA, we have the same, we have different mean, but the same covariant. But for QEA, we have different mean and also different covariant matrix. So that's why we now have subscript K, which indicate that this is class specific. Okay. The rest are the same. Right? The calculation are the same, and here this is how the density function look like, and this is how the discriminant function look like, and the class boundary now are quadratic curve. Why is it quadratic? Does anyone know? Yes.
Because we have the x, in the left term we have the x twice, and outside to the covariance matrix for the current class from the left and from the right.
Here, right?
Yeah.
Is quadratic in x. Right? So that's why we call it quadratic. So we don't have this term in classical linear, right? That's why we call it linear, but now it's become quadratic. Right? What are the number of parameters that we need to estimate in this case? So we have more parameters. Why do we have more parameters? Because now we assume that sigma can be different across all classes, right? Does it mean that is LEA more flexible than QDA? Which one is more flexible?
QDA is flexible because we have more parameters.
Yes, because we have more parameters, right? So we can basically play with the model, right, by changing more number of parameters. Right? So as an example, right, if we have 4 predictors and the number of classes is 2, LEA has 18 parameters, but QDA has 28 parameters. For P equal 8, if we have 8 predictors and the number of classes is 2, LEA has 52 parameters, but then QDA has 88 parameters. So we have now more parameters to estimate, right? But this also means that now we have more flexible models, right, compared to just LEA. And this is the example, right? So in this case, we have 2 classes problem, right? For this data set, we have that sigma 1 and sigma 2 are the same. So the data are generated from 2 Gaussian distributions with the same covariant matrix. Okay. And this dotted line basically represents Bayes decision boundary. You can see that Bayes decision boundary will represent the true, well, not the true, but the best decision or the best classifier if you know the true probabilities. Okay. It's linear, right? And this represents the decision boundary of LEA. This represents the decision boundary of QDA. It's curved because now it's quadratic. Okay. So you can see that if the underlying, Bayes predictor is linear, then LEA perform much better than QDA, right? But on the other hand, if you have 2 different covariants, if the data are generated under 2 different covariants, then the Bayes predictor, right? The best predictor, if we know the two probabilities, will be nonlinear, right? And in this case, using LEA will be sort of worse than QDA. Okay. Can we reason about this in terms of, you still remember bias and varying trade-off? Can we reason about bias and varying trade-off in this case? Okay, so LEA and QDA, let's compare these 2 models. LDA has less number of parameters. Doesn't mean it has less bias or less variance. Less variance. Why? It's not flexible, right? Because it's not flexible. If you change the data set, it's just gonna stay like that. But it's have high bias. Why?
In the data, it might affect the model.
Well, if you change the data, that's variance. Right? If you change the data, and if this thing changes, it means that it has high variance. But it has high bias because the model is too simple. Cannot model maybe non-linear function. Right? But how about QDA? It's larger variance one because of more flexibility. Is if you change data, then it's more likely that this function will change. But it's had less bias. Why? Because now it's more complicated, more flexible. It can model sort of non-linear function. Right? So this is well coming back to the question that someone asked at the beginning, right? How do we control the flexibilities of the models? Right? And you control the flexibility of the model by making all these choices about the model. Right? Should I use logistic regression? Should I use linear discriminant analysis? Should I use QDA? Right? All these choices, imply, right, or entail different flexibility of the models. Right? If you think that the data that you're working with is highly nonlinear, then maybe it's not the right choice to use LDA, right? So you want to maybe try to use maybe more complicated model like QDA. So that's the first ingredient when you work with machine learning models. You have to make some choices. And sometimes these choices, cannot, there will be no right choices. And sometimes these choices are subjective. But later in the following lecture, we will look at some of the techniques that we can use to automatically learn the right choices from the data. We can actually use the data to help pick what model we should use. Okay, and the way that we basically estimate QDA is basically the same as LDA, right? The only difference now is that we just need to estimate more covariant metrics. And that's how you estimate the mean. That's how you estimate the covariant metrics of the LDA. And this is covariant class benefit covariant metrics. This is how you compute the prior. And I'm gonna skip this slide because this is basically the simplification of the classification, but I can go through it very quickly. So usually to simplify the calculation, we use the eigenvalue decomposition of the covariant matrix. And given the covariant matrix sigma k, we can write sigma k as a product of metric UK, dk, and then UK transpose, where UK is an orthogonal matrix, and dk is a diagonal matrix that consists of a decreasing value of eigenvalue of this covariant matrix. Right? And why this makes things a little bit easier to compute, because if you plug this quantity back into the formulation that we have, right, you can compute everything in terms of the orthogonal metric U, which usually consists of eigenvector, right, and this diagonal matrix. So before you have to compute the inverse of this matrix. But now you only have to compute the inverse of this matrix. But you know that D is a diagonal matrix. What is the inverse of that diagonal matrix? No, it's not the same. The inverse of the diagonal matrix is just the matrix of
transpose?
Yeah. So if I have 2 by 2 matrix and if a diagonal consists of 2 and 2, then the inverse of this matrix will be 2 by 2 matrix with 1/2 as the diagonal. So you just compute the inverse of the diagonal entry. And it's easier to do than compute the inverse of the entire matrix. And this makes it easier. Yeah, so basically you can use this formula to compute the LE and QDA models. Right? I'm gonna skip this 2 steps. Okay. Let's spend the last 7 to 8 on looking at different scenarios, right? We now have learned 4 classifiers. We have learned KNN, nearest neighbor, linear discriminant analysis, QDA, and logistic regression. Now the question is, when should we use which classifier? So I'm going to show you sort of a bunch of scenarios, right? That basically we apply these classifiers in different kind of data set that we generate. Then we compare the performance of this model and see what are the trade-offs we are dealing with. Okay. So this logistic regression and LVA are actually very closely related, because if you write out the log on of LVA, you get something like this, right? Which looks similar to logistic regression. This is for logistic regression, you compute a log on. Yes, but they're different, because logistic regression we use maximum likelihood to estimate parameter, but for LEA we make assumption that the density function are Gaussian. Then we estimate the parameter of that density function. Yeah. Yes, and KNN neighbor is non-parametric and tend to work better for strongly nonlinear setting. And I think in the previous lecture, we compared the difference between KNN and linear regression, right? And the different in terms of assumption that they make. Right? So linear regression make the assumption that everything in the world looks like a linear function. The nearest neighbor assumes that, everything around you is locally constant. Okay, let's look at the first scenario. So in the first scenario, we have 100 random training data set. Right? In this case, we have 2 predictors. And we have 2 classes. So it's a binary classification problem. And we have 20 observations per classes. Okay. Not to make the confused. So we have 100 training data set. For each data set, we have 20 observations per classes. That means we generate a bunch of data sets, right? And then apply these models, right? And in this case, observation in different classes are uncorrelated normal variables with different mean and the same variance. What does it mean here? It means that this actually matches the LEA assumption. Right? The assumption that the density function is Gaussian and also have the same variance across 2 classes. And then basically that's why you see that LEA compared to, if we compare different classifiers in terms of test error, you see that LEA performs quite well. So just ignore CB here. So CB here is just cross validation. We haven't looked at this, but it's a different way of choosing the number of neighbors that we should do. So KNN1 is just KNN that look at the one nearest neighbor. Here you can see that LEA work very well, right? Logistic regression also work well because it's a so linear decision boundary, right? It's competitive compared to LEA. KNN and QDA. They are slightly, well, QDA are slightly worse than LDA. And logistic regression, but for KNN is much worse. Now we look at the second scenario. Like the setting is similar, right? But like scenario one, right? Here we assume that predictor in each class have a correlation of 0.5. So it's not going to be a symmetric Gaussian distribution anymore. Now we have a correlation. And the observation is basically similar to what we have seen before, right? LDA logistic regression and QDA perform equally well. Okay, so now we're going to make things a little bit more complicated. So let's say X and X2 are now generated using P distribution. It means that now it's no longer Gaussian distribution. The true distribution, the underlying distribution, are no longer Gaussian distribution. Then, in this case, the decision boundary is still linear, but the setup is still violate the LDA assumption. And what happened in this case, you can see that now LDA perform worse than before, right? And logistic regression now perform better. QDA all over the place. Because, and this is basically simply because the underlying distribution are non-Gaussian. And when this assumption is violated, non-linearity just makes things worse. And this also gives the observation that if your distributional assumption is violated, usually the linear model is much more robust to this kind of violation. Yes, so the logistic regression perform best, QDA not so good. And that's exactly because of non-normality of the data. Now, the next scenario, class 1 is normal distribution with correlation 0.5, class 2 normal distribution with correlation minus 0.5. What does it mean? It means that now the covariance metric between the two classes are different. So now this is exactly the assumption of QDA, but not LDA, because LDA assumes that we have the same covariance metrics. And that's why we can see that now QDA perform much better than the rest. Next. So we have two normal distribution with uncorrelated predictor. We have input x1 square, x2 square, and x1, x2, but not x1 and x2. Now the decision boundary become quadratics. And then when the decision boundary become quadratics, again QDA perform best, right? And k-nearest neighbor now follow. But the key observation is that now this linear model, LDA and logistic regression, now perform worse than QDA and KNN, which are non-linear models. Okay, I think this is the last scenario. Okay, in this case, we sample the response from a complicated linear function. Okay. I don't really know how the data look like, but in this case, we construct the example in such a way that the KNN would be able to model it. Right? Because although the function is linear, we construct it in a way that is so complicated enough that even when we use linear model, it's not going to work. But when we use KNN, it's work better. What is the takeaway in all these examples? Sorry?
Always choose logistic.
Always choose logistic. Good. That's the takeaway. No, actually, the takeaway is, we never know the underlying data distribution. And I can show you this because I know exactly how the data are generated. But in practice, you never know how the data distribution look like. So choosing different model, imposing also different assumption that you use. And that you have to keep in mind because whenever you use LDA, you make some assumption about your data. When you use QVA, you make some assumption about your data. When you use KNN, you make some assumption about your data. And you have to be, you have to understand what assumption you're making because when things go wrong, it means that some of the assumptions that you make are violated. That will help you identify the problem in your application. So that's it for today. Thank you very much.
Hey, I have a small question. What if we now have categorical predictors? Can we still do LDA and QDA by coding them? Because I think that
You can do it, but right. So but it's not going to be Gaussian distribution.
Yeah.
Right. You have to use different. So for Gaussian distribution, you assume that it's continuous.
Can we even assume some kind of distribution when we have categorical predictors? Can we even define some kind of distribution from?
There exists distribution for categorical data. For song.
So then when our assumption of Gaussian is probably violated, then probably LDA performs better than QDA. You know, categorical predictor? Or is that?
You mean when the particular
We have
data?
categorical predictors and we don't have our assumption method
Yeah, yeah.
Gaussian, and then probably LDA is more robust.
So you can generalize LDA to different distribution, right? You don't have to assume that it's Gaussian. If it's not continuous, it's categorical. You can assume different distribution, and then use that distribution.
And then you have a
calculate.
slightly different formula also?
You have slightly different formula, right? Because now the parameters are different, right? You have to
Yeah.
estimate different parameters.
Thank you.
Yes. Hey.
What is exactly meant by prior probabilities here?
Yeah.
Okay, so.
Sorry?